welcome to you to the third day of the workshop. And I hope you are enjoying the sessions and you have learned a lot about language models, NLP, in the last 2 days. And today we'll be moving to the second application area of deep learning and generative AI, that's in computer vision. So today I'll be basically talking. In the previous lectures, the experts they have introduced to the various areas of generative AI, but they have not talked in depth about what these models are. So today I'll be talking about GANs, their application areas, and we'll be also doing a hands-on session on GANs. And I hope at the end of this session you'll be able to implement your own GAN. So shall we start, participants? I hope you're ready, and I'll just share my presentation. Thank you so much. Hello, is my screen visible?
Yes, ma'am.
Yes, ma'am, it's visible.
Okay, thank you. So, today I'll be talking about generative adversarial networks, the architecture of these networks, and the intricacies of these networks and their application areas. But before we start, I'd like to show you some picture here. So, this is, can anybody tell me what this picture is? Or have you seen it on internet or so? Participants?
Looks like a Greek statue, maybe.
Okay, so this is not a tradition a picture of generated by a human artist, but it's a French art, and that has been developed by a group of people called people who formed a group called Obvious, and they generated this portrait using generative adversarial networks. And why this picture became, or this art piece became famous, was not only for its unique look, but because it was the first AI artwork that sold at a major auction house in US in 2018 for some 4,32,500 US dollars. So that was the, you can see the power of generative AI in creating these photorealistic pictures and in creating such artworks. So, although some newer models, yesterday in the last session, we have seen about diffusion models. So, we have OpenAI's Delhi, and which are also generating digital art pieces, but they have yet not been able to produce a piece that has matched or surpassed the auction price of this art piece called Edmund de Bellamy. So, another thing before we move to GANs is we all must be using these online shopping websites like Myntra, Nika, and recently in last 2 years you must have seen that these websites have introduced their try on option where they allow you to see how you look after wearing a certain selected clothing item. So again, that is, this virtual try on technology has been possible because of these GANs, or the generative adversarial networks. And we must have also used these Snapchats, and where we allow use different filters, and we also the, put these horns on our heads or goggles on our eyes or so. So all these things, they have been possible because of these generative adversarial networks, which we also call as GANs in short. So, if we look at GANs are one of the most influential architectures in generative AI, and they were introduced by a scientist called as Ian Goodfellow. And I hope most of you must be knowing about Ian Goodfellow. He's said to be the father of deep learning, and he introduced GANs in 2014 and which revolutionized how machines generate realistic arts. So, the reason for choosing this topic is it is one of the foundation stones in your generative AI, from where actually generative AI started. So, I think understanding GANs provides a solid foundation for grasping new generative AI concepts. And this is still a highly active research area with innovations like cycle GAN and style GAN, which are actually being used in your real world problems, which I just mentioned. So I hope with this lecture, you will be able to get a basic understanding of how GANs work and you will be able to use them for your own applications. And one of the other reasons for selecting this topic was very recently, if you have heard about Neuro IPS, that's a Tier 1 conference in machine learning. This is Neural Information and Signal Processing Conference. It awarded uh, two very prestigious awards to two papers. One was this, the paper by Generative Adversarial Nets by Ian Goodfellow and his team. And the reason was this paper has been cited more than 85,000 times as of now. So, considering this as the foundational stone for generative modeling, this was the another reason why I selected this topic for today's talk. So we'll start with what actually your GANs are, the model, how they work, what are the loss functions used, what are the problems with GANs, how you can overcome these problems, and then we'll go to the practical implementation of these GANs. So basically, if you can see on the slide, we have two types of models. One is the discriminative models on the left side, and the other ones are the generative models. So what is a discriminative model? So discriminative model is one that typically is used for classification in ML. So it helps you to distinguish between classes, such as you can distinguish between cats and dogs, and these are often called as classifiers. So the purpose of these discriminative models is to model the probability of class Y given set of features X. That is, we provide our model with a set of features X and we want our model to predict the class of this input X, which we call as Y. So, and on the other hand side, we see generative models. So what is generative model doing? So it is trying to learn how to make realistic representations of some classes. So let us say we take some input, some random input noise. Just a second. Let me take out my pen. So am I able to write? Is it visible on the screen what I'm writing?
No, ma'am.
No? Just a second. Let me rotate it. There's some problem with the writing pad. Just a second, please. So I'll reconnect my writing pad. Just a second. So is it visible now, what I'm writing?
Yes, ma'am.
Yes, ma'am.
So now suppose let us take some random input noise vector 3, -5 and 2.6 and which we call as psi symbolically, and we provide a class information that is, let us say I want to produce images of dogs, and given these two inputs to the network, it tries to produce some realistic features of a dog, of how a realistic dog might look. So it will produce an image of a dog. So why this noise is? So noise is basically to ensure that what's generated is actually not the same dog each time. So what we see is generative models, they try to capture probability distribution of X given different features of X. That is, they give different features of X given the input Y and the noise psi. Now, if you want to generate same images of dog, means if you want to generate only images of dog class, then you can skip this conditional probability Y and you can simply provide noise to the system and it will generate you a set of features X. So, if you look at these generative models, so two of the most popular classes of generative models are variational autoencoders, and the second one is generative adversarial networks. So, I'll just give a brief introduction to what variational autoencoders are. So, again, variational autoencoders they work with two models. One is the encoder, and the other one is a decoder. Both are neural networks. So we feed realistic images into the encoder, and then the encoder's job is to represent this realistic image into some latent space. And then the decoder, it picks up some points from this latent space and again transforms it into another realistic image of a dog. So basically, here again, the input is a dog and the output is also a dog, which resembles the original image. But in between, what we are doing is we are encoding our input into some latent space, and the decoder is again transforming that input from latent space into a realistic dog. Whereas GANs, they work differently. Again, GANs have two models. One is the generator model and the other one is a discriminator model. And again, both of these are again neural networks. And generator, it takes as input some noise and outputs some image of a dog. So it's taking a random noise, outputting a dog. And then over the time, what is this discriminator doing? This discriminator, as the name says, it's trying to discriminate whether this dog is a real dog or whether it's a fake image of a dog. So the purpose of this discriminator is to distinguish whether the image that it is getting, it's a real image of a real dog or a fake dog. So over the time, each model tries to catch with each other, and basically they are competing with each other. And what is these muscles? They are actually depicting that the generator and discriminator, they are both competing with each other or they are playing a game with each other. And so over the period of time, they learn with each other until they reach a point where we don't need the second model called the discriminator, and the generator can just take random noise and produce realistic images. So during the training, both the models are involved. Once trained, we can use this generator to generate images resembling the realistic examples, just like an artist that can paint paintings that can look like photos. So here again, this slide shows that what is here on the left hand side, the generator, it is trying to learn to make fakes that look reals. And the discriminator, it learns to distinguish real from the fake. So here you can see the ones in this, we can say the ones represented by green, those are the images generated by the generator or the fake ones. And the purple ones, have the images having purple boundaries, these are the real ones. So the discriminator, it learns to distinguish the real from the fake. And over the period of time, the generator will gain such an expertise that it will try to make fakes that actually looks like real, and the discriminator would no more be able to distinguish between the real and the fake. So that is what our purpose is, to create realistic photos from the given images. So if we look at what is the goal of the two networks, so the generator's goal is to fool the discriminator, whereas the discriminator's goal is to distinguish between real and fake. And over the process of learning, they learn from the competition between each other. And the ultimate goal is to make fakes that look real. Participants, is the concept clear? What actually the GANs do? So we'll move ahead and see what actually a discriminator is, what is the model architecture of discriminator, and what is the model architecture of generator. So discriminator is basically a classifier. So it learns the probability class y given features x. So what is the discriminator actually receiving? It is receiving an input image, which we call as x, and it is producing an output y, which is nothing but whether the image is real or fake. And these probabilities, which are produced by the discriminator, they actually serve as feedback for the generator. And from those probabilities, the generator learns how to improve it self over the period of time. So, actually, what classifies is, so I'll be talking about some basic concepts as well during the lecture. So, because we have people from different backgrounds, from different interdisciplinary fields. So I'll be talking about the basics as well in between. So what classifiers actually are? So classifiers are models that learn to distinguish between different classes. So here, as you can see, we have provided a picture of an image. So this classifier will basically extract features from the image, and it will tell whether this image is a turtle or a bird or a cat or a dog or a fish. So that is, it will give the probability of these. So maybe you will get some probability of 0.05 here, zero point 0.15 here, zero point 0.8 here, and so on. Again, 0.05 and 0.05. So what we see is that the cat class, it has got the maximum probability, and we can say that this is a picture of a cat. So it's not only that that the input to a classifier can always be an image. You can also provide a text to the classifier, and such as like it mows and plays with yarn. So these are two textual features that you have provided, and the classifier will say that this is a cat. So the basic purpose of classifier is to distinguish between different classes. And the classifiers, they model the conditional probability that is given a set of features x as input. They try to model the class probability y as output. So let us see how these classifiers are actually trained. So this is basically a classifier, and or we can say a discriminator. So let us see first what are the symbols that are used. So X is representing the features that we are providing as input to this discriminator. So, and then theta is basically the parameters of this classifier, what we also call as weights. And the classifier, while mapping these features X to the labels Y, it is actually updating the weights. So while we are training the classifier, or the classifier is learning, what is actually changing in the network or in the model is the weights of the model. So given a set of features X, the discriminator model, it predicts the class Y hat. So this is basically the actual, or we can say, oh, sorry, this is actually, just a second, what is happening? Just a second. एक second. I don't know what is the problem with this. If I'm writing something, the slides are changing. Just a second. So y hat, basically there's some problem with the writing pad. I'll leave it aside. So y hat basically is the prediction of the discriminator. And this cost function is what? This cost function is basically calculating the difference between the predicted output y hat and the class label y. So class label Y is, we said that this is a cat. So actually, when we are talking of classifiers, we always train them on some labeled data set. Labeled data set means what? That these labeled data set means that with each training input, there is a feature map or and the class label associated with it. So the cost function will basically calculate the difference between y hat and y, and then it will provide this as feedback to the network, and this discriminator will then update its parameter theta. So again, discriminator, it will tell you given a feature. So here you can see to this discriminator, we have provided a fake image of Mona Lisa, and it tells that the fake class has probability 0.85. So this is what the discriminator is actually telling. Now, next model that we have is the generator. So basically generators, it is the heart of GAN and it is used to generate images of a certain class. So if you will train it for class of cat, it will do some computation and produce different images of cats. So here you can see the input to this network is actually a random noise and the output is an image of a cat. So here you can see as we provide different noise to the network is producing different outputs at every run. So it is producing different images of cat every run. So unlike discriminator, which is just giving you the probability that whether an image is real or fake, the generator, it outputs an image. So let us see how the generator actually works and how the generator improves over time. So basically, again, we will provide a random noise vector to the generator, and this random noise vector will then be passed to the generator, which is a neural network, which will produce a set of features that can pose an image of a cat, which we call as X hat. So this X hat is basically, can you just please wait for 1 second so that my writing pad works again? Why is it not working? Parak, can you please come to my room? So this X hat is basically an image of a cat which has been generated by this generator, which is then passed to the discriminator. And this discriminator will actually produce an output Y hat, which tells whether the image is a real or a fake. And this Y hat will then be compared to the actual output, which is y, and the cost function will be computed. But now this time the cost function will be passed to the generator to update its weight, and this time only the generator will be updating its weight. So as I told you, how good or bad your discriminator is, this feedback will be provided to the generator, and the generator will use this feedback to improve its learning parameters theta. So once you have designed your generator or you're trained your generator, then you can save your generator. You can provide different noise vectors, and then you can produce different types of images that you want. So basically, the generator, again, it is given the class information that whether it is to produce an image of a cat or a dog, and then it is producing that image. So the input is basically random noise and the class information whether I want to produce an image of a cat or a dog, and the output is a set of features which represents a realistic cat. So now, once we have seen the basic models of generator and the discriminator, we'll be now looking at what is the loss function that is actually being used here. So in the loss function, I'm not able to write on this.
Okay, okay.
So just see what I maybe I pressed this button or
Okay.
it's not writing. And I wanted to write something. So it's just changing slides.
Okay. Okay. Even team, I'll figure it out.
Okay.
Okay, ठीक है.
है ना? You see it on your this laptop, है ना? Connect it and then give it to me. You can take this.
Yeah.
So basically in this BC, this is the binary cross entropy function that is used by the GANs. And we'll see what are the different components of this binary cross entropy function and what are the problems that this binary cross entropy function actually causes in the functioning of GANs. So here the first thing that you can see on the left hand side, you have 1 by m. Your 1 by m is basically the batch size. So whenever you train your model, you're training it over not over the entire training data set, but over batches of the training data set. So we compute the loss of the model over the complete batch, and that is why we have taken this summation here. Now here yi is the actual label of the input, that is whether it is a real image or a fake image. This h xi theta, this is the prediction of the model. So this prediction of the model is on the basis of the input that it is receiving, and theta is the learning parameters of the model. So the prediction will actually depend upon what your input to the model is and the learning parameters are. And theta is basically the parameters and xi is the features. Now we'll see there are two components in this BCE cost function and what each of these represents. So if we look at the first component, that is yi into log hxi theta, this is basically relevant when the label is 1. That is when you are presenting a real class image to the discriminator. Because if you are providing a fake image, then its label will be actually 0. Then its label will be basically 0. So the second term will become irrelevant. So first is when you are providing a real image to your discriminator. So if your yi is 1 and hxi theta, that is the prediction of the network, is also close to 1, then we will see that the first term will be nearly equal to 0. But if you're providing an image of real class, but the discriminator is not able to figure it out and it is saying that it is a fake image, in that case, the first function will evaluate to minus infinity. So when the prediction and the label actually match, the loss will be near to 0. And when the prediction and the label, they are far off from each other, then the loss function will actually be infinity. So the second term of this BC cost function, this is relevant when the label of the image is 0. That is when we are providing a fake image. Actually, it is a fake image, so its label will be 0. In that case, again, we can see that this term of the BC cost function, if the label is 0 and the prediction of the discriminator is also near to 0, then this loss function will be near to 0. But if the label is 0 and the prediction of the discriminator is real, that is the two are not matching, then again the loss function will be large and it will be near to infinity. So here we can see graphically also how the loss function is changing. So again, if you can see the top left corner of this graph, so this shows basically on the left hand, on the x-axis, we have the prediction of the discriminator. And on the y-axis, we have the loss function. So we have plotted the loss function versus the prediction of the discriminator network. So basically, you can see if the prediction is far from the actual label, which is actually 1 year, you can see the loss is very high. It is approaching infinity. And as the discriminator improves, what is happening? That the prediction is actually close to 1. That is, for a real image, we wanted the prediction to be actually 1. And in that case, we can see on the right corner, you can see right bottom corner, this cost function actually it approaches 0. So similarly, we can see for the second term, that is when we are providing our discriminator with a fake image. So in the fake image, again, you can see if the prediction is matching, that is, your prediction is also 0 and the label of the image is also 0, the cost function will be near to 0, as you can see from the bottom left corner of the graph. And if the prediction is 1, that is, it is far from the actual label, which is 0, you can see the cost function, it approaches infinity. So in both the cases, we can say whether we provide our discriminator with a real image or a fake image, if the prediction is close to the actual label of the image, the loss function will be near to 0. And if the prediction and the actual labels are far from each other, then the loss function will be approaching to infinity. So we can see that the BCA cost function, it has two parts, one relevant for each class. And this will be close to 0 when the label and prediction are same. And it approaches infinity when the class and prediction are different. So those who have already worked on classification problems using deep learning, this BCE cost function, that is the binary cross entropy function, this is one of the most commonly used loss function for binary classification problems. And here also our discriminator is doing binary classification only, that is telling whether the image is real or fake. So next we'll come to training of GANs. So if we'll see this complete model as a whole, so we have two models, generator and discriminator. Generator takes the noise, it produces fake images X hat, and these X hat plus the real images X, they are fed to the discriminator, who then distinguishes the fakes from the real. It produces the output Y hat. This is how actually the GAN models work. So now we'll see how actually the GANs are trained. So to train a basic GAN, you alternate training on generator and discriminator. That is, you do alternate training. First you train generator, then you train discriminator, then again generator, discriminator. So the discriminator output is always, or the loss is always fed as input to the generator, and it tells us in which direction to move. So here we will see generator. Again, it takes as input random noise, produces fake sample called X hat, which are fake images. And then these generated images X hat along with some real images are passed to the discriminator. The discriminator then generates probability Y hat, and this Y hat is then compared with the actual labels of the images. So the discriminator computes the binary cross entropy loss function, and this is used to update the weights of the discriminator. So discriminator first updates its weights, and at this point of time we are only updating the weights of discriminator. So theta d, as you can see on the slide, those are representing the parameters of the discriminator model. In the next phase, as I told you, we do alternate training on discriminator and generator. So again, generator, it generates few fake samples X hat using random noise input. And these are again passed to the discriminator. Discriminator again makes prediction. And after computing the cost, the gradient is then back propagated and the parameters of generator are updated. So basically, in a neural network, if those who are aware of neural networks, backpropagation is the most fundamental algorithm that is used for weight updation or parameter updation. And this backpropagation algorithm, it basically uses gradient descent rule, where you change the weights using the negative of the gradient of the cost function. So here in this GANs, you can see the cost function is actually the cost function which is produced by the discriminator. And this cost function is actually passed as input or back propagated to both discriminator to update its weight, and it is also passed to the generator to update its weight. But here, as you can see in this slide, we are training the generator of part of the GANs, and only theta g. Theta g means the parameters of the generator are updated. So you alternate this training only one model at a time while the other is held constant. So over the period of time, both the generator and the discriminator, they try to match the skill of each other. And so it is very important to keep in mind that both models should improve together and they should be kept at similar levels from beginning of training. Now, what happens if we have a discriminator which is much superior than generator? That is just very, very good at predicting that all fake samples that it has been provided are fake. Then this will provide no useful information for the generator. So generator doesn't know how to improve and it doesn't know in which direction to go or update it, wait, and the learning will stop. So we want neither the discriminator should be superior nor the generator should be superior. But if we look at these generator and discriminator, can you tell me which is more easier to train? The generator is basically generating an image given a random input noise, and the discriminator is a classifier which distinguishes between real and fake images. Can anybody of you tell me which is easier to train? Hello? Anybody from the participants? Participants? So basically, okay. So if you will look at this, discriminator is much easier to train because it has to just figure out whether the input that has been provided to us is a real one or a fake one. Whereas the generator is difficult to train because it has to model the entire feature space of what an object should look like. So suppose you want to produce images of cats, then you have to model the entire feature space of how actually cats look like. So it is generator is much difficult to train as compared to the discriminator. So to conclude, we can say that GANs, they train in an alternating fashion. And the two models, they should always be at a similar skill level for the models to improve. Hello, can you please mute your mic, Srinivas Khedkar? Okay, so we'll continue. So until now, we have seen the basic model architecture of GANs. What are the architectures of your discriminator and your generator models? And what is the cost function that is used by GANs? And now we'll be seeing what is the problem with the GANs, because of which there was a need to develop newer models. So those who are familiar with GANs, they must have heard about mode collapse. So let me go to the presentation. Just presentation from current slide. Just a second. So what are the problems with GANs? So basic GANs, they suffer from two problems. One is the mode collapse problem, and the other one is your vanishing gradient problem. And we'll see why these problems arise. What is the cause of these problems? So let us talk about mode collapse and what actually a mode is actually. So if you look at the diagram on this left hand side, you will see there is a mode which had been shown, an arrow showing a mode in this data distribution. So basically, mode in a data distribution is an area with high concentration of observations. So for example, in this figure, you can see a normal distribution of data, and the mean of this normal distribution can be considered as the single mode of that distribution. Whereas the figure on the right hand side, we can see it has two modes and we can call it as a bimodal data distribution. Multimodal data distribution means which has multiple modes. So basically, if we say what a mode is, any peak on probability data distribution of the features is a mode of that distribution. So where you are having high concentration of observations, that is basically a mode of that data distribution. So you can have data distribution where you can have multiple modes as well. So here, this figure actually shows the different modes of a handwritten character recognition system. So we have, say, these 10 handwritten digits from 0 to 9, and these are represented by features x1 and x2. That is, these are the two dimensions which are used to represent numbers from 0 to 9. And we can see that this probability data distribution has many peaks corresponding to each digit. So probability data distribution in this case will be surfaced with many peaks corresponding to each digit. And we can see that this is a multimodal data distribution having multiple modes. So if you can see, there is a box showing sevens and the data distribution has been associated with it. What is it actually showing? It is showing multiple observations of digit 7, which will be represented by similar x1, x2 values. So those digits which are having similar values of x1 and x2, they are representing the data distribution of one digit. Similarly, the data distribution of 5 is shown by another data distribution. So this is again data distribution having 10 different modes corresponding to each digit. Now we'll see what actually mode collapse problem is. So suppose let us take a discriminator which has learned to be good at identifying handwritten digits that are fakes. So this discriminator, it can distinguish whether this handwritten digit is fake or real, except for certain classes like ones and sevens. So it knows that this 2, 0, 3, 8, and 9, these are all fake images produced by the generator. Whereas the images of 7 and 1, they look realistic to the discriminator, although these are also fake images. So discriminator, it classifies most of the digits correctly except for the ones that resemble digits 1 and 7. And this information is passed to the generator. Generator sees this and it looks at the feedback from the discriminator and it gets an idea of how to fool discriminator in the next round. So suppose you are given an exam, आप उसमें कुछ आंसर्स लिखते हो एंड द टीचर कैनॉट कैच द रॉन्ग आंसर सो यू नो कि टीचर ने ये आंसर ढंग से नहीं देखा है तो मैं इस तरह के सिमिलर आंसर्स और लिख सकता हूँ एंड आई वोंट बी कॉट सो सिमिलरली दिस इज व्हाट इज हैपनिंग हियर so discriminator is provided with fake images of multiple digits. It can recognize most of the digits as fake except for ones and sevens. Now this generator, it gets this feedback from the discriminator. How it is getting? It is getting the loss function of the discriminator as feedback. And now it knows that for the digits 1 and 7, the discriminator is not able to catch the fake ones. So what is look is This generator now, from next round onwards, it starts producing images of digits 1 and 7 only. It will now not produce any other digit except ones and sevens. So over the period of time, again discriminator learns that these are fake images of sevens, but still it cannot distinguish between fake and real images of ones. And again the generator gets to gets to know this information. And what the generator does now is the generator now only produces images of digit 1. So what is it doing? Only producing digit 1. It is not producing fake images of any other digits, whether it's 2, 3, 4, or so. So what has it happened? The generator has collapsed to only one single mode in the data distribution. If you remember in the previous slide, I'll just go back here. We had a data distribution which had 10 different modes corresponding to each digit. But now what has happened is the generator, it has collapsed to only one mode and it is now only producing images, fake images of digit 1. This is what we actually mean by mode collapse. Over the period of time, it may happen that the discriminator may learn to distinguish between fake ones and so. But again, the generator, it will collapse to some other mode. This is not what we want from our generator. We want our generator to produce a variety of images of different classes. So we want diversity in our output. We just don't want one single class image produced every time. So this is one of the major drawbacks of your GANs. So to conclude, we can say that modes are peaks in the distribution of features. And this is a very typical case observed in real world data sets. And mode collapse happens when the generator gets stuck in one mode. So another problem that I talked was of vanishing gradients problem, that the your GANs, they also suffer from vanishing gradient problems. So what we see is BC loss functions. This causes mode collapse as well as vanishing gradient problem. So here, if we see, we'll start with how actually this problem occurs, vanishing gradient. So the main objective GANs is to make the generated and the real distribution look close to each other. And of course, during the whole process, the discriminator is trying to delineate or it is trying to distinguish between this real and fake distribution as much as possible. So what we are trying is we want to move the generated distribution close to real one, but the discriminator is trying to delineate or distinguish between the twos. So if we look at the GANs, the discriminator's task is just to produce a single output, whether the image is real or fake, and it is much easier to train than the generator. However, this generator, it produces a complex output, that is it producing a real image, and it is difficult to train. So often the discriminator, it gets better than the generator over the period of time. So in the beginning of training, the discriminator isn't that good and it has trouble distinguishing the generated and real distributions. And there is some overlap and it is able to give useful feedback in the form of non-zero gradient back to the generator. So as you can see the figure on the left side, it is showing that the generated and real distribution, they have certain overlap and the discriminator is not able to distinguish between these two. And what we can see is that it can provide useful feedback to the generator over this. Participants, I'll just take a break for a minute. I'll just connect, my writing pad is working. So just Okay, participants, we'll continue. My writing pad was not working, so I've taken this break. So it's now working. So, okay. So we were talking about what is the problem with the BC loss function and how it causes the gradient descent problem. So as you can see, initially our discriminator is not well trained and there is some overlap between the generated and real distribution and it cannot distinguish between these two. And here we can see that it can provide useful gradient back as input to the generator and the generator knows how to improve. Now, but as the time proceeds and the discriminator starts getting better at training, it learns to delineate. Delineate means it learns to distinguish between the real and fake distributions. And now you can see the gradients, they might get closer to zero. And this does not provide any useful information to the generator. Gradient is zero means, and we are using backpropagation algorithm. This means the generator will not get any useful input. It won't be able to change its weight and it will be stuck in a local minima. So it doesn't know how to improve. And this is how vanishing gradient problem occurs in your GANs. And this is mainly because of the use of the BCE loss function. That is the binary cross entropy function. So we can say that the GANs, they try to make real and generated distributions look similar. And when the discriminator improves too much, the function approximated by BC loss function, it contains flat regions. And that these flat regions, they actually correspond to vanishing gradients. So to overcome this problem, there was another loss function that was introduced, which is also called as Wasserstein loss function, which actually uses the earth mover's distance. And this cost function, it can overcome the problem of your vanishing gradient, which was found in the basic GANs. So this earth mover distance is actually measures the distance between the two distributions. And so let us take these two distributions. We have the generated distribution on the left side, and we have the real distribution on the right side. So we can see that these two are normal distributions and they have same standard deviation, but their means are different. So this earth mover distance, actually it measures the effort needed to make it measures the effort needed to make the generated distribution equal to the real distribution. So it actually depends upon the distance and the amount moved. So it is actually calculating the this distance between the generated and the real distribution. So if we look at this graph again, so with BC loss function, what we have seen, I'll go back to this. So as the discriminator is improving and it is increasing the distance between generated and real distribution, the gradient becomes close to zero and there is no useful feedback to the generator. But if we look at the earth mover's distance, as this difference between the generated and the real distribution increases, there is no as such ceiling. So there is no as such ceiling. If you look at the BC loss function, it was actually approaching 1. So the gradient here was 0. So as such here, there is no ceiling on the value of the cost function and it grows regardless of how far apart these distributions are. So gradient of this measure or of this earth mover's distance, it would never approach 0 and this function will never contain flat regions as observed in the BCE cost function. And hence, if we use this earth mover's distance, we can actually remove the problem of vanishing gradients, which was there in your basic GANs. So we can again, let us start with the BC loss function and then we will define the Wasserstein loss function, which is based on earth mover's distance. So in the BC loss function, we had two parts. One was for the real images, and the other one was for the fake images, the right part. So basically, this can also be simplified as this is the expected loss of the discriminator over a real image. So X here basically represents real image, D represents the discriminator, and what is the output of the discriminator over a real image and expected values of those. Now, if we look at the right part, it is basically actually telling D is the discriminator, G is the generator, and Z is the noise. So it is basically telling what is the performance of discriminator over an image generated by a generator G when it takes as input noise. So I'll again repeat the right part of this function. It actually tells what is the expected loss of the discriminator when it receives a generated image from generator which takes as input noise Z. So here you have two parts, one for the discriminator performance over real images, one for the discriminator performance over the fake images generated by the generator. And in this process, the discriminator, it is trying to minimize the loss. So here you can see MIND means what? Discriminator wants to minimize this loss. It wants to distinguish between the reals and the fakes as much as possible. Whereas the generator, it wants to maximize this loss. That is, it wants to fool the discriminator and it wants to make the fakes actually look like reals. So this is basically a min-max problem. So basically when you will search for the loss function of GANs, you will find this equation and it is called as a min-max function. Why? Because one network or one model discriminator is trying to minimize it and the other one is trying to maximize it, and this is called as min-max gain. And we want to reach an equilibrium, Nash equilibrium in this min-max gain. So let us see about this W loss which helped us to overcome the vanishing gradient problem caused by the BCE loss function. So W here stands for Wasserstein loss, and this Wasserstein loss approximates the earth mover's distance. So rather than using the symbol D now, here we are calling our discriminator D as a critic. So C here basically is nothing but the discriminator which is now called as a critic. And we are seeing what is the performance of our discriminator or the critic on a real image and what is the performance of our discriminator or the critic on a generated fake image. So as you can see, again this some. So again, here the discriminator is trying to minimize this, whereas the generator is trying to maximize it. So the discriminator, it wants to maximize the distance between these two. So here in this equation, we are seeing earth movers distance, which is the distance between the generated real distribution, between the real distribution and the generated distribution. So this is my real distribution and this is the generated distribution. So my critic C or the discriminator C, it wants to maximize this distance, and the generator G, it wants to minimize this distance. That is, it wants the fakes and the reals to look similar. Is it clear? So this is your Wasserstein loss function which uses earth mover distance, the distance between the real distribution and the generated distribution. As there are no logs in this loss function, as you can see, there will be no problem of vanishing gradient. Now, if we look at the discriminator output, in our BC loss function, our output was 0 or 1. That is, this Z is basically the output. So it used sigmoid activation function, the values between 0 and 1. So here, if the value of the output of the neuron is greater than zero point 0.5 and lies between zero point 0.5 and 1, the output would be this 1, otherwise it would be 0. So here the outputs will be restricted to 0 and 1. Whereas if we are using Vostisin loss function, we don't want our output to be between 0 and 1, and it can be in any real value. So our output layer neurons, they need not use sigmoid activation function. They can use any linear activation function. So this is the basic difference between BC loss and W loss. And W loss, Vostisin loss, it helps us in solving the problems of mode collapse and vanishing gradients, which occurred due to BC loss. So now we'll move to another type of GANs, which are called as conditional GANs. So if we look at basic GANs, so you can look here on the slide, we have a gumball vending machine. So basically what do? You put a coin in this vending machine and you get outputs from a random class or a random ball you may get. So you put a coin and you may get a green colored ball. You put another coin and you may get a yellow colored ball. You put a coin and you may get a blue colored ball. You put a coin and you may get a red colored ball. So what it is doing, every time you put a coin, you are getting a different colored ball. And if you want, suppose if you want only a red color ball, you have to spin this every time you have to input a coin, spin it, and maybe by chance you may get a red colored ball, or again you have to repeat the process. Similar is with our GANs. So in our GANs, the generator, it may produce an example of any random class. We cannot say that generator, you produce this particular class. So it may, if we do not guide it, it may produce unconditional, it may do unconditional generation, and it may produce images of any random class. So what we can do is, we have another class of GANs, which is conditional GANs. That is, we are conditioning our generator to produce output from a particular class only. So again, if you remember, we provide a noise vector as input to the generator, and this noise vector basically ensures randomness in the generation. That is, you don't get the same image every time, you get a different image. That is why we are using a random noise vector. Now, if we want to control the generation, suppose I want to produce images of different dog breeds, and let us say I want to produce image of a husky dog breed. So I have 7 classes of dog breeds, and I want to produce an image of husky dog breed. Then I can also provide a class vector as input to my GAN or to my generator, which will then produce only images of husky dog. So I put in this class vector, I put 1 in the position of husky dog, and for all other classes I put a 0. So now my generator, it will produce only, so here in this slide you can see, I have concatenated the class vector along with the noise vector, and this input is now passed to the generator, and it will produce an image of a husky dog. So again, it might produce, as you put different noise vectors to the generator, it may produce different images of husky dogs. Now, this was about the generator, how we can control generation of images of a particular class. Now, how does the discriminator know images, what class images this generator is producing. So we need to pass this class information to the discriminator as well, so that it knows ki what particular class information this generator is producing. So suppose if we, this is basically a picture of another class of dog which is called as beagle dog. So we have provided a fake image, we have provided a real image of a beagle dog to this discriminator, and the class information is that of golden discriminator retriever. Let us see what will be the output of the discriminator. The output of the discriminator will be 5% real. Why this is happening? I said I provided a real image of a beagle dog, which is different from this class information, which is golden retriever. So what happens is the discriminator, it will only consider an image as real or fake only if it is of that class golden retriever. So even though I provided the discriminator with a real beagle dog image, its output is 5% real. That is, this is again fake image of a golden retriever. Now suppose I provide an image of a golden retriever, and the class information that I am providing is also the same, golden retriever. The output of the discriminator will be 98% real. Why? Because although it was a fake image of a golden retriever and the class information is also golden retriever, the discriminator can tell that this is a golden retriever image. So how do we provide this class information actually as input to the discriminator? So if you can see the input to the discriminator, our discriminator is what? It is basically a classifier. And to this classifier, we are providing an RGB image. That is a red, green, blue image, or an image having 3 channels. So which are two-dimensional matrices. So what I can do is, this is actually my image, red, green, blue, and to this I attach or concatenate a one hot class vector. And how is this vector actually concatenated? We have matrices of zeros and ones of the same dimension as the input image. And suppose this is the class for which we want to generate images. We will keep it as all ones, and for all other classes, these matrices will have all zeros. So this is how we pass the class information to the discriminator. So we concatenate this one hot class vector with the image and pass it to the discriminator. So those who have used these deep learning models, so basically you provide 3 channels as input, 3 channel input to your classifier. Now rather than 3 channel, we are providing 3 plus 7 these channels, so 10 channel input as input to the discriminator. So this is what I have already told to you. So now let us come to the basic applications of GANs. So where GANs are actually being used. Some of the applications I have already discussed with you when we started our presentation. So GANs have found to be super cool for image to image translation task. So basically this is an example of a super resolution GAN. You are given an original image that is a very low resolution, and you pass it to a super resolution GAN and you get a much higher resolution GAN from that. So in many applications, like in medical imaging, you have a lot of blurry images and you want to make them higher resolutions. So using a GAN, you can create much better sharp images as compared to traditional upsampling techniques. So, if we talk of image to image translation, it isn't about just going from one domain to another domain or there's one to one mapping. In fact, there is multimodal image to image translation as well. So, here in this slide, you can see we are given a picture of a cat and you can map it to different breeds of dogs. And so this is really cool because the model doesn't actually know what classes of dogs there are, and it can map a cat to different breeds of the dogs from your training data set. So other than image to image translation, you can also use GANs for text to image translation. So basically you are given a sentence such as the bird is black with green and has a very short beak, and the GAN can generate various images that match the sentence. We have seen this task yesterday also while ma'am was discussing about diffusion models. But this is where the idea came from. So stack GANs were already in place, and this is from where they started applying those diffusion models and started generating text images from the text actually. And in fact, the earlier versions of DAL-E, ma'am talked to you about DAL-E 3, but the initial versions of DAL-E, they started with stack GANs only, and then they switched to diffusion models. So basically, you can also do image to video translation. So as you can see here, you are given an image of Mona Lisa, and you can take a video of someone else talking, and you can extract various face landmarks from their face, where the eyes, eyebrows, nose, mouth are, and then you can input to your model both the image of Mona Lisa and the face landmarks of some other person that you have extracted from some other video, and then you can create talking heads of Mona Lisa. So this is what we have heard of Harry Potter talking paintings. So this is how they generated talking paintings. So you take an image, you take face landmarks from some other video, and then you create talking heads. So another application area which all of us might have used on our mobile phones is image filters such as those on snapshots. So here you can see a person being turned into a lemur, or you can add some makeup, or you can change how people look like. So many beauty companies like Nykaa and all, they are using these GANs for trying makeup before you actually buy it. So virtual try on by Myntra is also an example of similar kind that I discussed in the beginning. So another cool application of GANs is image editing. So you are given an image and you are given a mask of this image. Mask is basically telling, or if you can see, you have different colored regions. So this is telling different classes that are present in your, or different image features that are present in your image. So what we can do is we can change this mask a little bit. So what you can see is we have changed this mask of hairs of this person, and using this we can now generate. So we have edited the mask and we have generated an edited image of this person. So we have used such kind of things in our, or the children at your home must have used such kind of image editing softwares on your mobile phones. So from research point of view, if we look at the application area, one of the most important application areas of GANs has been for data augmentation. Data augmentation basically means generating synthetic images of your data set, or for increasing the size of the data set and for increasing the diversity of the data set. So from one single image, as you can see here, this we have one single image, and from that we have generated so many similar kind of images. So this helps us to increase the size of the data set and the diversity of the data set. And then you can use this augmented data set for downstream tasks like classification, segmentation, and you can improve the accuracy of your model. So GANs, they have also been used in medical related areas, such as this is an example of stimulating tissues from a state of the art GAN. So here you can see this GANs has generated patches of tissues, and even a board certified pathologist cannot distinguish between the simulated GAN generated tissues and the real ones. So even in one of our papers, research papers, we have applied GANs to generate synthetic histopathological images. And then we have used the augmented data set for improving our classifier accuracy. So this is one another cool application of GANs, which is around climate change. So in order to show the visceral effects of climate change, so we can grab any street view image, such as on the left hand side, you can see an image, a real input of a street, and then you can superimpose of this how the street will actually look if there is flood in the city. So the right hand side is actually showing the generated output if flood actually occurs. So the people who are working in climate change, they can visualize the effects of global warming and so and depict it to the people. So, in summary, we can say GANs, they can be used for image to image translation, and they can be used for many different tasks, including text, audio, and media in different modalities. So, with this, I would like to stop at this point, and uh, I'll end my first presentation where I have introduced you to the GANs and some of the applications of GANs. And in the next session, we'll be talking about how to implement GANs. And before implementation of GANs, I'll be discussing some of the basic operations of CNNs, convolution neural networks. And then we'll see one implementation of a basic DC GAN, that is deep convolution GANs. So I'll just stop presenting. And participants, if there are questions, hello. Sorry, I couldn't see your messages earlier, Seema, Vaibhav, and Pratibha. So, any questions, participants? So, shall we take? So, Srinivas, unknown attack detection. We can use these adversarial mechanism that is used by GANs for the adversarial concepts of GANs for attack detection. So it's not that we use GANs only for image generation, but the concept of this adversarial nature of discriminator and generator, they can be used for attack detection. Any other questions? So he's asking how to use GANs in real-time traffic classification. So basically, traffic classification is a different problem. We are not doing classification here in GANs, but in real-time traffic classification, what one of my students is doing is, if you have this you can generate synthetic your is a traffic sign detection or traffic classification. Srinivas, can you elaborate a bit on what you are actually trying to say? Traffic classification.
Hello.
Hello. Yes, Srinath.
Yes, ma'am. Actually, I want to know that can we use GAN with some IDS modules, like IDS tools, like maybe some Snot or something like that, and using that hybrid of the machine learning models with the real-time IDS tools. Is it possible to have that kind of amalgamation here?
So you can use the basic purpose of GANs if you are talking of classification problems is for data augmentation. If for a particular class you don't have sufficient samples, earlier people used to use these upsampling techniques for generating synthetic samples, but now you can generate synthetic samples using GANs for any classification problem.
Right. But beyond that, can we have the use of these GANs in the real-time applications like detection of traffic or in that sense classification of the network traffics?
So for classification, you need classification models only, Srinivas. But you can definitely augment your data set. So basic application of GAN in your application would be for augmenting the data set. So if you have an imbalanced data set, there you can apply GANs for data augmentation.
Okay, thank you.
Okay. Okay. So I suppose no more questions. So, Parak, do you want to say something?
Yes, ma'am. So I wanted to ask. So we've heard about mode collapse, and you also explained about it a little bit. I wanted to ask, like, on an industry level, how is it mitigated on large scale applications?
Mode collapse in large scale applications. Particularly, I couldn't get your question, but mode collapse is actually this is a problem in GAN. So we can use conditional GANs where we can, if we want to generate images of a particular, then we can train our GANs for different types of classes. So that is what we used earlier when we used it for one of our agriculture related project where we had to do plant leaf disease detection. We were having the same problem of mode collapse. That is the same class images were being generated. So we then applied the concept of conditional GANs in that case, where we conditioned our generator to generate a particular class image, and then we used trained it separately for the multiple classes that we had.
Okay, ma'am, I
So
got
I
it. Got it.
don't
That
got it
clarifies it.
what mode collapse you are talking in terms of industry. Your mode collapse is basically the generator is generating only one type of image or one class of images only. That is basically what we mean by mode collapse here in GANs.
Yeah, ma'am, got it. I think that clarified, no doubt.
Okay, thank you. So participants, we'll take around 5 to 7 minutes break, and then again we'll continue with our discussion on GANs and implementation of GANs. Yes, Amisha, you have a question? Hello.
Hello. Good morning, ma'am.
Good morning.
Ma'am, I have a question about how the DD gang is compared to ReLU gang, and how the quality and the image and the stability of the image will enhance if we use the DD gang instead of the gangs.
DD GAN is basically a hybrid model that you're talking of, a combination of diffusion and your GANs, isn't it?
Yes, ma'am. Denoising diffusion gangs.
Yes, denoising diffusion GANs. So basically, you can again in that. What are you trying to ask me in that? Basically, that's an hybrid model where you are generating images using your denoising diffusion model, providing it to the GANs. GANs is basically providing you feedback whether it's a real or a generated fake image, and then you use that to improve the image quality. So that we have to explore. Matlab in research area, I have not exactly seen the architecture of DD GANs and what is performance in compared to vanilla GANs. So that is a research thing that we need to explore.
Okay, ma'am. Thank you.
Okay. Okay, see, we'll join back in another 10 minutes at 11:40. see an implementation of DC GANs, I'll be discussing basics of CNN for GANs. And I suppose from the sessions that I've attended in the last 2 days, people have not discussed much about CNNs. And CNNs is one of the most popular models in your deep learning, which you use for classification, for segmentation, and here for generation also. So it's, we can say, one of the fundamental models of your deep learning. So I'll be starting with basic of CNNs, and I'll be discussing only those which are relevant to GANs, and then we will see an implementation of DC GAN. So how many of you are actually familiar with CNNs? Hello, participants, can you just, other than Parak, what about the other participants, the outside managed participants and all? Have you used CNNs in your work, research work, or in your applications? Okay. So I got one more response, not much. So I'll be starting with few basics of these CNNs, and then we'll move to its implementation, its use in GANs. So basically, the most fundamental unit in your neural networks is your neurons. And what your neurons does is, first it, so if you look at this one particular neuron, it is receiving inputs from multiple other neurons. So what each neuron does is, it computes weighted sum of the inputs that it is receiving. So here, before we move ahead, let us see what these symbols mean. Here are, L is basically the layer number. So we are basically talking of, when we talk of neural networks, we generally talk of layered architectures. So L here denotes the layer number. I here denotes the neuron number, and this activation is the output of this neuron, and Z is the input net input that this neuron is receiving. So basically, this neuron is receiving, this ith neuron of layer L, it is receiving inputs from the previous L minus 1 layer. So what it will do is, it will first do weighted summation of the inputs that it is receiving. So ZIL is nothing but the weighted sum of the inputs that it is receiving from the previous layer. And then over this ZIL, it will apply some activation function. So here on the next line, you can see actually G is the activation function that you are applying over this net input. So we had many other activation functions in neural networks, but I'll talk the ones which are relevant to your CNNs and which we'll be using in our GANs. So this G, this can be any mathematical function, but two desirable properties are, first, it should be differentiable. Why it should be differentiable? Because we are going to calculate gradients of these output values. So it should be differentiable. And second, it should be non-linear and continuous. If it is not non-linear, we will not be able to model non-linear complex input values. Or if it is linear, we will just simply downscale to a linear regression task that we will see in the next slide. So activation function, it can be any mathematical function which is differentiable and which is non-linear in nature, so that we can model complex and non-linear inputs. So this I have already told. If your in this activation function is not non-linear, then we cannot compute complex features. And suppose, let us see this neural network. We have a layer, these three layers of neurons. The input layer is never counted as a layer. So this is my first hidden layer, this is my second hidden layer, and this is my output layer. So it's a three-layered neural network. And if these neurons are basically using linear activation functions like identity function, this neural network will simply scale down to linear regression problem, where you are having a linear function between y and X. So that is not always case with real life data sets. There is not always linear relationship between input and output, but there is non-linear relationship. So if you are providing your neural network with an image of a person and you want the name of a person, so there is not linear relationship. That is a non-linear relationship between face of a person and the name of a person. So we'll see now some of the popular activation functions that are used in CNNs. The first and the foremost one is the rectified linear unit, which we also call as ReLU. So this rectified linear unit, it produces maximum of 0 and ZL. ZL is what? The net input to the neuron. So if your net input to the neuron is positive, which you can see by this blue line, the output will always be positive. And if your net input is negative, if you can see this purple line which I am redrawing, retracing, the output will be forced to 0. And this forcing the output of the neuron to be 0 when net input is either 0 or less than 0, this causes a problem in the ReLU function, which you call as the dying ReLU problem. So as your net input becomes 0 or less than 0, the output would be 0, and hence some of the neurons in the network may die and may not contribute to the functioning of the network. And this is what we call as dying ReLU problem. We won't be able to pass any useful gradient to other neurons, and our network may be stuck somewhere and it may stop learning. So, to solve this problem of dying ReLU, we had another activation function which is called as leaky ReLU. So, now here you can see this g of z is equal to max of alpha z comma z. So, if your net input, which is z, is actually positive, again the output of the neuron will be positive. But if your actual input to the neuron is negative, then again the neuron, it will produce some output. So there will be certain this slight gradient which this neuron will actually produce, which is shown by this purple line. But this would be quite small. So the value of alpha, it is generally taken to be zero point 0.1. So let us suppose our z is -1, then max of this g would be what? Max of minus zero point 0.1 comma minus 1. So you know this is minus zero point 0.1 is smaller, so it will produce an output minus zero point 0.1. So it will still continue to produce small output so that our gradient, it doesn't become equal to 0, and this will solve the dying ReLU problem. So rather than using simple ReLU, in most of your CNN networks, you will be using leaky ReLU as the activation function. Then another very popular function is your sigmoid activation function. So as you can see, sigmoid has a very smooth shape and its outputs value between 0 and 1. So when z is greater than 0, so here is, you can see on the x-axis we have the value of z, which is your net input to the neuron, and on the y-axis we have the output of the neuron. So if you can see this, if the net value z, it is greater than equal to 0, the output will be in the range 0.5 to 1. But here again, what problem happens is, as your z increases and it approaches infinity or it becomes extremely large, this output of the neuron or the output of this function, it also starts saturating to 1. And this causes vanishing gradient problem in your, so again the gradient will become 0 here, so it won't be able to pass any useful information to other neurons. And again, in this part, you can see in this lower quadrant, you can see if z is less than 0, then the output will lie between 0.5 and 0. Again here, as your net input, it starts approaching large, extremely large negative values. Again, your output will saturate to 0. and this will again cause the vanishing gradient problem. So your sigmoid function, it basically causes vanishing gradient problem because its derivative approaches zero at the tails of this function. So it asymptotically approaches zero at the bottom and it asymptotically approaches one at the top. So this is one of the problems in your sigmoid and why we don't actually use it in the hidden layers of our CNN models. We may use it at the last layer when we have to do classification. There we can use the sigmoid where we want our values to be between 0 and 1. But in the hidden layers, we generally avoid sigmoid activation function because it causes vanishing gradient problem. So this is my tan hyperbolic activation function, which is very similar in shape to sigmoid, but it outputs values between -1 and 1. So if you can see in sigmoid, the output lied between 0 and 1. Here the output lies between -1 and 1. So if you have positive input to the neuron, the output will be between 0 and 1. If you have negative input to the neuron, the output will be between 0 and -1. So again, here you can see at the top right and at the left bottom. Again, you have flat regions and this causes the same issues that we have seen in sigmoid. The saturating, the function saturates to +1 and -1 and again causes vanishing gradient problem. So if you want your output to be output of the neural network to be +1 -1, there you can use tan hyperbolic, but don't use it in the middle layers or in the hidden layers. So now we'll see what actually the basic operations of your convolution neural networks are. Convolution. So what convolutions are and how they work. So convolutions are useful layers for processing images. They scan the image to detect useful features, and convolution is a very simple operation where you do just element wise product and sums. So let us see what a convolution is. So this is an image of a dog which you see on the left hand side, and on the right hand side we have a this we pass a eye filter. Now what do we mean by an eye filter? A filter that will search in the image where eyes are present. So what do? You take this filter and you pass it through different portions of the image where the eyes will be present. This filter will give you highlighted output, and when the eyes are not present it will give you a lower output value. So just like eye filter, you can use a nose filter, you can use an ear filter to detect where the eye is present, where the nose is present, where the ear is present. So these filters are basically looking for features in your images. So convolution, it helps you to extract features from your input image. And because you have different features in your image like eye, nose, ear, you can use different filters or multiple filters, scan, pass through your image, and you can get the features of your image. And what these filters actually are now, you will say. So these filters are nothing but 2D matrices consisting of some real numbers. How these 2D matrices actually, what computation that they do, that we'll see in the coming slide. So let us take a 5 cross 5 grayscale image where each square is a pixel with value between 0 to 255. Here 0 represents entirely black and 255 represents entirely 1. And let us convolve it with a filter. So here you can see there is a filter which has all ones in the first column, zeros in the middle column, and -1 in the rightmost column. Now, when you do this convolution operation, now you can see as I move through the slide. So first, this filter will go to the topmost corner, and this filter will be multiplied with the values of this grayscale image, and then you will sum it up. So you can see first we have done element wise product of the filter with a portion of the image. Then we have calculated the sum, and this is how in the result we get value 150. Then you again stride your filter. Striding the filter means passing the filter to different portions of the image. There is something also called as receptive field. Receptive field means how much large portion of an image is covered by a filter. So this is a 3 cross 3 filter. So at a time it can see only a 3 cross 3 portion of your image. Now here I am striding my filter by one. One means I am moving one step ahead each time, left from left to right, and then I will move it from top to bottom. So again I get value 150. Then I again stride it to the top right portion and I get value 0. Then again I move the filter down. So again left to right, then top to down. And this is how, using this convolution operation, I get the resultant matrix as shown in the slide. So what is this resultant matrix actually showing? This filter is actually detecting a vertical line in your image. So if you can see this, this top left, this top, left side of your, the entire left side of your image is actually a vertical line. And when you pass your filter through this image, you actually detect a vertical line in the result as I am highlighting. Can you see it? So this is just one example where I am detecting a vertical line. So in your image, there may be many complex features, many edges, many other things which may be present. So you may pass different multiple filters to your image and get different feature maps of your image. So this is just one feature map of your image, which is showing one vertical line in your image. So next operation that we'll see is the pooling operation. So after this convolution, we apply a ReLU layer. That is, once we do the convolution, we apply an activation function over this result, and then we apply pooling operation. So basically, what is the purpose of pooling? It is used to decrease the dimension of the input image by taking mean or maximum values of different areas. So here in this slide, you can see there is a picture of this cat, and after a pooling layer, there will be a resultant blurry image with lower resolution. So pooling is just trying to distill information. Distill means get out the meaningful information from your feature map. So there are different pooling operations like max pooling, min pooling, average pooling. So here we will see an example of max pooling. So again, you are given a 4 cross 4 image and you reduce it to a 2 cross 2 output image by visiting different sections of the image and selecting the maximum value it in. So just like you slided a filter. So what we will do is we take this, if you can see the red boundary, 8 minutes. So what we can do, I'll just highlight. We take a 2 cross 2 filter kind of thing. And in this, we try to find the maximum value. So in this part of the matrix, the maximum value is 20. So we fill this 20 value here. Then we again stride this. And what do we get? We again get this 30. We stride it by 2. So again, we are looking at this portion. So we get value 45. And then we get 10 from this area, and then we get the maximum value 43 from this area. So by what amount you will stride your filter of max pooling, that will depend upon what is the resultant size of the image that you want. So what is the desired output size? Depending upon that, you will apply the stride. So here we have applied stride 2. This means from here we skipped first to this. Then from here we skipped to this. This was our stride 2. So there are other types of pooling as well. Average pooling. What average pooling will do is it will take or it will find the average of 0, 28, and 1. Min pooling will find the minimum of this. So it will do 0. So max pooling is the most commonly used pooling operation because it helps us to extract most salient information from the feature map. So one different thing from pooling and what we did in convolution, if you remember convolution, I'll just go back to the convolution slide. We had these filters, and these filters were nothing but a matrix of real numbers. And this is a learnable parameter. What do we mean by a learnable parameter in a model? Something which is learning during the process of training. So these filter values, these will change over the period of time as our network learns. So during the convolution operation, when we'll apply backpropagation, the filter will values may change. But max pooling, here we are simply finding the maximum value in a particular region of the image. Here we do not have any learnable parameters. So this is how it is different from your convolution operation. Participants, I hope the difference is clear. So the next operation that I am going to discuss is upsampling, because we'll be using upsampling for image generation. So your generator, it basically uses the upsampling or transposed convolution operation. So that is why I'm discussing this operation here. So upsampling has the opposite effect of pooling. So given a lower resolution image, upsampling produces a higher resolution image. And one way to upsample is to use a method called as nearest neighbor method. So what will nearest method do? So basically again we are given a 2 cross 2 input image and we want to upsample it to a 4 cross 4 output image. So with upsampling what we will do is we pick this value 20 and we fix it here in the top left corner of the output image. And then the neighboring pixels of this 20, they will be filled with the same value. So this is a method called as nearest neighbor upsampling. We may have other methods, interpolation or bilinear interpolation methods that you can use. But this is the most commonly used method. That is why I've discussed it here. Then we pick up this value 45. We again stride by 2, fill this square with 45, and again its nearest neighbors will be filled by 45. Then these will be filled by 10, and these will be filled by 40. So the distance, now you will say how we decide the neighbors. So the distance will depend upon by how much ratio you want to upsample here. So here we just wanted to double the size of image. We had a 2 cross 2 input and we wanted it to double it to 4 cross 4. So this, depending upon this, we decided that these neighbors will be only the adjacent neighbors of 20. So this neighbor distance will depend upon the size of an enlargement you want. So this is the same output that I have drawn earlier. So there are other types of upsampling techniques like linear interpolation, bilinear interpolation. So the next operation that I am going to cover is transposed convolution. So some of your GANs, they used upsampling techniques, some used transposed convolution. There is some problem with transposed convolution, and that is why we avoid them in GANs. We'll see that problem also. What is that problem? So now that you are familiar with pooling and upsampling, we'll see how transposed convolution works. And In your pooling and upsampling, you are not using any learnable parameters. But here in your transposed convolution, you will use a learnable filter to enlarge the size of the input. So basically, it's a similar technique as upsampling, but here you will use a learnable filter to upsample your image. So again, let us take a 2 cross 2 input that we want to upsample to a 3 cross 3 output value. So again, we will take a 2 cross 2 learnable filter and we will stride it through this. So what we will do is, we have this input 1. This input 1 will be multiplied by this filter. So what do you get? 1 cross 2, 1 cross 2, 1 cross 1 and 1 cross 4. So please see the values which I am 1 cross 2, this 1 cross 1 and 1 cross 1. This is when I am applying this filter to this leftmost top left value in the input. So what do I get? I get these values. Now I stride my filter by 1 and now I again multiply by this filter with the next input value. So when I do this again, I will get 4 cross 2, 4 cross 2, 4 cross 1, 4 cross 1. Just see the values that I am circling. So these are the values that you get when you move the filter or stride the filter by 1. Now again, you use this next input value, again stride the filter by 1 and you move it down. So again, what values do you get? 0 multiplied by 2, 0 multiplied by 2, 0 multiplied by 1 and 0 multiplied by 1. In the squares which where we are getting multiple values, what do? We simply sum these values. So here you can see this pixel is being affected by this filter twice, this filter, and this pixel at the center, this is affected by the filter or it is involved in the computation 4 times. So this is how actually your transposed convolution works. So you are just doing upsampling, but upsampling here is done by the means of a filter which can learn the values during the process of training. So here, as I told you, I'll just try to clear these values. So if you can see, some of the values are influenced once, while some of the values at the center, they are influenced by all the values in the input. तो अगर आप बीच वाला जो सबसे हमारा मिडिल पिक्सल देखेंगे, ये इनपुट इमेज के हर पिक्सल से अफेक्टेड है, जबकि ये वाला देखें, ये सिर्फ एक ही पिक्सल से अफेक्टेड है, ये वाला एक पिक्सल से, ये वाला एक, ये वाला एक, ये वाले 2 पिक्सल से अफेक्टेड है। और इससे क्या हो रहेगा, कुछ पिक्सल्स में हैवी वैल्यूज आ जाएंगी। हैवी वैल्यूज मींस कुछ पिक्सल्स ज़्यादा इंटेंसिटी के हो जाएंगे और कुछ पिक्सल्स कम इंटेंसिटी के हो जाएंगे। एंड दिस इज व्हाट कॉजेज अ प्रॉब्लम कॉल्ड एज checkered board issue. So what I have shown, what I was saying just now, this pixel is influenced by 1, the pixel in the middle is affected by 4 input values, and this causes checkered board problem. So like you have seen a Chinese checkered board, तो कुछ pixel values बहुत dark हो जाएंगी और कुछ बहुत light रहेंगी, and this is the problem which we see in transposed convolution. So transposed convolutions, they are used for upsampling, they have learnable parameters, and they suffer from the checkered board pattern problem. So next thing, another important layer that we are going to use in building our GANs is your batch normalization. So if we look at GANs, they take a lot of time to train, especially if you want to build them for really cool applications like the ones we have seen for synthetic image generation, for style transfer, and so on. So the training of GANs isn't as straightforward as we do for normal classifiers. And the generator and the discriminator, they aren't aligned. So they both are moving in opposite direction. One wants to maximize the loss function, the other one wants to minimize the loss function. So we want to use every trick that can speed up training. And batch normalization is one such technique which has proven to be very effective. So let us see a simple neural network that takes as two inputs as variable x1 and x2. Suppose we want to use this neural network for classifying whether it is a cat or not. So let's say x1 is the color of the cat and x2 is the size of the cat. And let us see the distribution of these two input features. So this figure, it is showing the distribution of input feature x1, and this feature is showing the this figure is showing the data distribution of feature size. So here we can see that this distribution is better. We have very few extreme values while this distribution is skewed. So you have some higher values here, more higher values here, and the mean is also very high, and the standard deviation, the spread of this function is low. Whereas the standard deviation of this function is pretty spread and the mean is also average. So what how now we'll say why we are discussing the distribution of these input features, because the distribution of this input feature, it actually affects how our cost function changes, or what is the pattern of the changing of cost function. So again, the figure on the right, or the graph on the right, it is showing how the cost function changes over time with W1 and W2. That is the weights which are connecting X1 and X2 to the output. So if you can see, this graph is a little bit elongated. Elongated means that the changes in the cost function are not very smooth, and this causes the training to be low. So the result of we can say that the result of the distributions of these input features actually affects how our neural network learns. So it basically determines the speed of learning, or the way the neural network learns. So before we move to batch normalization, what we can do is, and another problem with these neural networks is you always train your neural network on a training data set, and then you matlab again put it into test for a test data set. But the distribution of training and test data set might be very different. So your neural network, it might be working good for your training data set, but it might not work for test data set. And that is what we call as covariate shift. That is the change in variation. Covariate shift means what? The change in data distribution causes the change in the cost function to be abrupt, or it does not cause it to be changed in a smooth way. This is what we actually mean by covariate shift. I'll again repeat that the change in the data distribution, it results in abrupt changes in the cost function, and that is what we mean by covariate shift. Just a second. But if we normalize our input variables x1 and x2, then the cost function will look much more smoother and more balanced. So if you can see here we have normalized x1 and x2. Their distributions were earlier like this, what we have shown here. And now when we normalize our inputs, we have zero centered the mean, and the standard deviation is also near to 1. So now our cost function looks more smooth, and the changes in the cost function will also be more smooth, and the learning will also be more smooth, and you will reach the minima of your this cost function faster as compared to when your data was not normalized. Thank you. So what we'll see how to actually normalize our this data set. So what do we do for each batch? We compute its mean. So here mu I, this is denoting the mean, this is denoting the standard deviation. And by normalization, what do? I have to bring my mean near to 0 and standard deviation near to 1. So I subtract the mean from the output value, or from the this z of each neuron, and then divide it by the standard deviation. That is what we do in batch normalization. And here, एक minute. So now, as I told you, this batch normalization you can use for your training data, because for the training data you have the entire batch of the training set that you're providing to the neural network. So you can effectively calculate the mean, you can calculate the standard deviation, and you can normalize your data. But what about the test data? For the test data, because when you have calculated the mean and standard deviation for training data, it was different. Now for the test data, it might be different. And test data you are providing as on the go. Not, you're not providing the entire batch of the test data for testing to your network. So what do? While you're training your network, you calculate the batch statistics, that is the mean and the standard deviation, and you use the same batch statistics while you're using the test data. So this is how actually batch normalization works, and its main advantage is in reduction of covariate shift. Covariate shift, I'll again repeat, changes in the weights with the changes in the data distribution. So we don't have to actually do this process. Frameworks like TensorFlow and PyTorch, they keep track of the mean and the standard deviation. And you simply have to use a batch normalization layer like we'll be using in our model. So, but just to give you what actually batch normalization is, what is its purpose, and how will it help in improving the speed of learning in our network. So with this, I am ending my introduction to your CNNs. We'll be using what all things I have introduced to you in this PPT. We'll be using this in our implementation of GANs. Okay. So I'll be again starting with building a DC GAN for handwritten character recognition. You can find this Python file on TensorFlow website, on Google Colab, and so. Is the screen visible to all?
Yes, ma'am.
So today I'll be using Google Colab to demonstrate this GANs example. And so it's a very popular platform for machine learning and AI development. And it offers you free access to GPUs and TPUs. So those who do not have GPUs at their organization, they do not have high-end AI workstations, They may run their models on Google Colab. Another platform is Kaggle. You may use Kaggle also to run your uh, Python scripts. So for today's lab session, I'm taking this script on Google Colab, and I'm using the TensorFlow framework for today's session. And if we look at TensorFlow, you have another this platform which you call as PyTorch. So TensorFlow and PyTorch, these are the two most popular platforms for implementing your deep learning models. So the basic difference between TensorFlow and PyTorch is that in TensorFlow you need to first define things and then compile. And PyTorch is imperative in nature. Basically, you can do computations on the go. So if you talk of computational graphs, TensorFlow they have static computational graphs, whereas PyTorch they have dynamic computational graphs. So you can use either of them, whichever is comfortable to you. So here I'll start from the beginning. So this is the start of this script. So we have not of pip install image io. So these are basically some libraries that you need to install if they are not already there. So image io is basically a Python library for reading and writing image data in various formats. And this TensorFlow docs, this is for installing the TensorFlow documentation. Now we'll come to the starting of this script. Parag, if you can enlarge that, because again, yesterday I've seen that if we open these scripts, they appear very small on the screen. Participants, is it visible clearly?
Yes, ma'am.
Okay, okay. So these are some standard libraries you need to import for your image generation or image classification task. So this glob library, this is for pattern matching in file paths. OS for interacting with your operating system, such as file and directory manipulation. Time for time functions. Then your image IO, this is basically for image handling and processing. So basically today we are going to see an example of generation of handwritten digits, and that is why we have used this library image io. So it helps you to read and write images in various formats. Then we also have this, if you can see, import pil. So pil is basically short form for your Python imaging library. So again, it is used for tasks such as resizing, cropping, or filtering images, opening images, and then your matplotlib. This is for creating visualization such as displaying images or graphs. So if you want to plot your performance metrics such as accuracy or some other metric, you might need some plotting libraries. And then you have this TensorFlow.keras. Now, what is this Keras? Keras is a high level library which has pre-built layers for building neural networks. So this is a special library provided by TensorFlow, which already provides you some predefined layers which you use in your neural network. So you don't need to actually define the function of convolution, how to do convolution, how to do transposed convolution or so. These layers are already available to you. And this ipython.display, this is for displaying dynamic images during your model training, which we'll be actually doing. So I'll be showing you how the generator generates different images at different time steps or different epochs of training. So that's why we have used these. So the first step in here is to, I'll highlight the text which I am explaining, is to is to load our data set. So what we are using here is MNIST data set, which is your handwritten digit data set. And so diff tf.keras.dataset. So this is already present in your Keras library, this data set. If you want to load data set from some external device or some Google Drive, you may do it in a different fashion that the other speaker will discuss with you today in the second half. Currently, we are using the pre-existing data set from Keras. So here again, we are dividing our data set into train. Extracting the train images and the labels. So this is a label data set. Label data set means with each image there will be a label, whether it's digit 0, digit 1, 2, 3, 4, and so on. So next we come to we want to generate images of size 28 cross 28. So that is why we have reshaped our train images to 28 cross 28. So this function train underscore images dot reshape is nothing but reshaping our image, because our GAN, it will generate images of size 28 cross 28. So we have rescaled our train images also to this size 28 cross 28. The next step that we are doing is basically we are normalizing our image pixels in the range -1 to 1. So this is just simple normalization. Then we have buffer size and batch size. What do we mean by buffer size? We may be having a very huge data set with suppose 1 lakh images or 10 lakh images, but your system may not be handled, or even the collab, it may allow you only a certain limit of memory quota. So it may allow only suppose say 50,000 images or 60,000 images. So again, Google Colab is a this cloud computing platform which offers you GPUs and TPUs. So along with processing power, it allows you only a fixed quota of memory. So this buffer size means I am only extracting 60,000 images from my complete data set, MNIST data set. Now, what is this batch size? Again, we will divide our training data set into batches of size 256. Now, those who are familiar with neural networks, actually, there are different modes of training neural networks. One way is either you provide your neural network with the complete data set at one go, यानी पूरी 60,000 images दे दो और आप incremental learning करो. Incremental यानी कि एक image दो, weight update करो. दूसरा होता है बैच मोड ऑफ ट्रेनिंग. बैच मोड ऑफ ट्रेनिंग मीन्स व्हाट? आई विल प्रोवाइड स्मॉल स्मॉल बैचेस ऑफ ट्रेनिंग डेटा सेट, एंड एक पूरा बैच प्रोवाइड किया, फिर मैंने वेट को अपडेट किया, फिर एक बैच प्रोवाइड किया, वेट को अपडेट किया. दैट इज व्हाट वी मीन बाय बैच मोड ऑफ ट्रेनिंग. सो हियर दिस बैच साइज इज बेसिकली टेल्स द size of the batch that you're providing it for training to your neural network. So then you have this train data set shuffle. So we are here in this, basically we are just creating batches by shuffling our images in the buffer. So out of 60,000 images, I will again shuffle it and extract a batch of T256. Again shuffle it and get. So basically how to do sampling from 60,000 to get a batch size of 256. That is what we mean by batch and shuffle the data. So once we have done this, we have prepared our training data set. Why we are preparing our data set? Because if you remember, to the discriminator, I need to provide both the real image as well as the fake image. So these real images which you are going to provide to the discriminator will come from this training data set. Now, as I told you in TensorFlow, you need to first define things, define the function, then call the function, define the model, then call the model. So here now, next we are going to see how to define our generator model. So this function which I have highlighted, here we are basically defining our generator model. ठीक है. So in the generator, if you remember, we passed the generator and input as input a random noise vector. Then from the random noise vector I get an image. How do I get an image? By upsampling that random noise vector. So how we are doing this? We again need to define our model for that. So make generator model, we are defining our generator model. The first line tf.keras.sequential, we are defining a sequential model. Sequential means a stacked layer of neurons. Then we will define the first layer. So the first layer is a dense layer. Now dense layer means a neuron, matlab a fully connected layer where each neuron is connected to every other neuron in the previous layer. So what is the input to this? So let us see here. We want to provide a noise vector of dimension 100, that is a row column vector of size 100 as input to our generator. So here if you will see input shape is equal to 100, this means we are providing a noise vector of size 100. And then in this dense layer we are reshaping it to a 7 cross 256. I'll draw on my slide what I actually mean by this. So this is basically, yeah, बन क्यों नहीं रहा है? What happened? I need to present online. So what I am doing is, एक minute बेटा. So this is a 100 sized vector, noise vector. So this noise vector you are drawing from some random number distribution of size 100, and then you are rescaling it or reshaping it into a 7 cross 7. And how many as such 7 cross 7? These are 256. So basically you are reshaping it into an image of size 7 cross 7 with 256 channels. जैसे कि आपकी एक RGB इमेज में कितने चैनल्स होते हैं? 3 चैनल्स होते हैं. यहाँ पे जो आपकी इनपुट इमेज है उसमें कितने चैनल्स हैं? 256 चैनल्स है. और इनपुट इमेज का साइज कितना है? 7 क्रॉस 7. तो आपने इस नॉइज वेक्टर जो कि अभी एक सिंगल कॉलम वेक्टर था 100 साइज का, 1 से लेके 100 तक की रैंडम वैल्यूज थी, उसको रीशेप कर दिया एक 7 क्रॉस इमेज में. इज इट क्लियर? So then once you have done this, then you use this batch normalization layer. So as I told you, batch normalization will do what? It will normalize the output of each layer. Then you add a leaky ReLU layer. So this is basically applying activation
मैम
function.
कुछ नहीं दिख रहा है.
नहीं दिख रहा है? एक सेकेंड. Oh no
नहीं
no.
मैम, ये बहुत
Actually
देर से हम देख रहे हैं.
मेरे
It's
में तो
visible.
सब वी आर एबल टू स्क्रीन. हाँ मेरे को भी वो दिख रहा है मेरे मोबाइल पे. अब दिख रहा है शिवेंद्र?
नहीं मैम, नहीं दिख रहा, अभी भी नहीं दिख रहा है.
आप एक बार रीज्वाइन कर लो शिवेंद्र, मे बी यू आर हैविंग
एक
सम.
मिनट, ठीक है ठीक है ठीक.
बाकी क्योंकि बाकी पार्टिसिपेंट्स को दिख रहा है एंड आई कैन सी ऑन माय मोबाइल आल्सो. मैं लैपटॉप से प्रेजेंट कर रही हूँ और मोबाइल में आ रहा है. परक, आर यू एबल टू सी? प्रतिभा परक,
Yes,
Yes,
ma'am.
ma'am.
Visible.
जूम करूँ मैं?
जी मैम, दिखने लगा.
दिखने लगा. एक मिनट मैं थोड़ा सा जूम कर लेती हूँ जिससे कि आप लोगों को ये दिखने लगे. हाँ फॉन्ट अब जूम कर लिया. अब दिख रहा है आप लोग को पार्टिसिपेंट्स? और जूम करूं? वन
अब
टाइम.
नहीं दिख रहा है, अब नहीं दिख रहा है.
भाई मैंने तो जूम करा है अभी सिर्फ. अब दिख रहा है?
शायद जूम नहीं करना था.
नहीं बट जूम करने से क्या प्रॉब्लम है?
No, ma'am, it's visible. It's visible nicely.
इट्स विजिबल. यस। बेटा आप फिर से रिकनेक्ट करो, मे बी सम प्रॉब्लम इन योर मीट। हाँ, नेटवर्क प्रॉब्लम हो सकता है, कभी कभी नेटवर्क प्रॉब्लम की वजह से वीडियो
जी मैम।
स्टॉप हो जाता है। ठीक है। सो एज आई टोल्ड यू, दिस इज योर डेंस लेयर। सो अभी तक हमने कोई प्रोसेसिंग नहीं की। नाउ वी अप्लाई बैच नॉर्मलाइजेशन। तो जो हमारी डेंस लेयर का आउटपुट होगा 7x7, उस पे हम बैच नॉर्मलाइजेशन अप्लाई करेंगे एंड देन वी एड एन एक्टिवेशन फंक्शन लेयर विच इज द लीकी रेलू लेयर। अभी भी हमारे पास जो हम अब हमारे पास आ रहा है मॉडल डॉट एड डॉट लेयर्स रीशेप। सो दिस इज नथिंग बट 7x7 विथ चैनल्स 256। तो हमारे पास ये अभी हमारे पास एक आउटपुट आया है। 7x7 का एक इमेज है जिसमें 256 चैनल्स हैं। एसर्ट जो फंक्शन है दैट इज नथिंग बट जस्ट एसर्टिंग की जो हमारी आउट लेयर का आउटपुट हो वो एक्चुअली में वो आए, तो वो सिर्फ एक sort of check है हमारे लिए. So that is not doing, assert is not actually doing anything. It's just asserting that the model output is of the shape as mentioned. Now once we have defined, तो अभी हमने अपने 100 साइज का जो नॉइज वेक्टर था उसको कन्वर्ट किया एक 7 क्रॉस इमेज में विद 256 चैनल्स. Now we are going to upsample this 7x7 and we are using a con 2D transpose. So now with this, now let us see. मैंने आपको बताया था जब हम ट्रांसपोज्ड कॉन्वोल्यूशन अप्लाई करते हैं, एक्चुअली वी आर अप्लाइंग अ फिल्टर देयर. अप सैम्पलिंग में हम कोई लर्नेबल पैरामीटर्स नहीं होते, कोई फिल्टर नहीं अप्लाई करते, बट ट्रांसपोज्ड कॉन्वोल्यूशन में वी अप्लाई अ फिल्टर. So now 128 का मतलब क्या है? 128 means the number of filters that I am going to apply. 5x5 means the filter size. जैसे कि मैंने आपको प्रेजेंटेशन में एग्जांपल दिया था, हम 3x3 फिल्टर यूज कर रहे हैं, 2x3. तो similarly 5x5 is the filter size. Stride is 1 means by how much amount I am shifting my filter. Padding same means what? Now here again, participants, I would like to draw your attention. When we use padding same in convolution operation, तो इनपुट और आउटपुट शेप क्या होता है? सेम होता है. पैडिंग का मतलब क्या होता है? आप जो अपनी, आई अगेन गो टू पीपीटी मोड. प्रेजेंटेशन चल रहा है मेरा सर, मेरा प्रेजेंटेशन चल रहा है. मैं प्रेजेंटेशन के बाद. So here, if you have an input of 4x4, padding same, and you apply a convolution operation, again you will get an output of 4x4. Generally हम convolution में क्या करते हैं? 4x4 का हमने convolution apply किया, हमको 3x3 या 2x2 output मिलता है. Normally convolution में depending upon how you are striding through the filter. 4x4 है और padding same का मतलब क्या है? That the output of the convolution operation will be same as input. And how that is possible? We are padding our image with some zeros. And what is the effect of this padding? कि जब हम filter slide करें तो हम इमेज के सारे पोर्शंस को इक्वली विजिट करें. जनरली क्या होता है, जो कॉर्नर वाले पिक्सल्स होते हैं, जो एजेस पे फीचर्स होते हैं, वो एक ही बार विजिट होते हैं और वो इतनी मतलब डोमिनेंस से सिलेक्ट नहीं हो पाते हैं. तो पैडिंग से हम क्या करते हैं? वी गिव इक्वल इंपॉर्टेंस टू ऑल द पिक्सल्स विच आर प्रेजेंट इन द इमेज, वेदर इट्स द कॉर्नर और द सेंटर ऑफ द इमेज. बट व्हेन वी यूज कॉन 2D, पैडिंग सेम मीन्स व्हाट? एक मिनट, I'll tell you what actually means. कॉन 2D हमें अप्लाई करना है. हमारे पास एक 2x2 इमेज है और इसको हमें ट्रांसपोज्ड कॉन्वोल्यूशन से एक 4x4 इमेज करना है. पैडिंग सेम से अब वो क्या करेगा? नाउ हियर व्हेन वी आर अप्लाइंग कॉन 2D ट्रांसपोज, मतलब ट्रांसपोज्ड कॉन्वोल्यूशन अप्लाई कर रहे हैं. It doesn't mean कि 2x2 से हमें आउटपुट 2x2 ही मिलेगा. It means that here with this padding, I will again give equal importance to these corners also, जिनको पहले नहीं मिल रहा था. And I will assert that my output size is 4 cross 4. So this is what is the difference of padding same in convolution operation and transposed convolution operation. I hope the difference is clear. We'll go quickly. Now, we have added one this. Now again, I'll come here. Assert model output shape. अभी भी हमने अपना जो output shape है वो क्या रखा है, एक 7x7 image है. But the number of channels have reduced now. पहले कितने थे, 7x7 image with 256 channels. अब हमारे पास 7x7 इमेज है बट 128 चैनल्स. तो विद द पीरियड ऑफ टाइम, क्योंकि हमें जनरेट क्या करना है, एक आरजीबी इमेज जनरेट करना है जिसमें सिर्फ कितने चैनल्स हो, या ग्रे स्केल इमेज जनरेट करना है तो एक ही चैनल चाहिए हमें, आरजीबी करना है तो हमें 3 चैनल ही चाहिए. तो हमें इमेज का डायमेंशन तो बढ़ाना है बट नंबर ऑफ चैनल्स क्या करने हैं, ओवर द पीरियड ऑफ टाइम कम करते जाना है. सो नेक्स्ट वी ऐड अगेन ट्रांसपोज्ड कॉन्वोल्यूशन लेयर. नंबर ऑफ फिल्टर्स 64 हो गए, साइज 5x5, स्ट्राइड 2, पैडिंग सेम. अब हमारा देखिए मॉडल आउटपुट चेंज हो गया है फ्रॉम 7x7. नाउ आई हैव जनरेटेड एन इमेज ऑफ साइज 14x14, बट द नंबर ऑफ चैनल्स हैज रिड्यूस्ड फ्रॉम 128 to 64. तो साइज हमारा डायमेंशन विथ और वो तो बढ़ गई हमारी लेंथ और विथ, बट नंबर ऑफ चैनल्स कम हो गए. अगेन वील ऐड अ बैच नॉर्मलाइजेशन एंड लीकी रेलू. हम फिर से एक और थर्ड कॉन्वोल्यूशन, ट्रांसपोज्ड कॉन्वोल्यूशन अप्लाई करेंगे. एंड दिस टाइम यू सी number of filters is only 1 and the output shape is also 1. So now I finally get an image of 28 cross 28 with only one channel, because I am using a grayscale, generating a grayscale image. Grayscale में आपके single channel ही होगा, RGB में 3 channels होंगे. तो आपने नंबर ऑफ चैनल्स इनिशियली कितने शुरू किए थे, 256. 256 से 128, 128 से 64, और फाइनली जो आप इमेज जो जनरेट करना चाह रहे हो उसमें कितने चैनल होंगे, 1, और उसका साइज क्या होगा, 28 क्रॉस 28. So using transpose convolution, I have upsampled an image of 7x7 to 28 cross 28. और हमने स्टार्ट कहाँ किया था, एक 100 साइज के नॉइज वेक्टर से, जिसको हमने रीशेप किया था एक 7x7 क्रॉस 256 के वेक्टर में. So this was about the generator model. So we have just created the generator model. We have yet not trained the generator model. So here, this we call our generator model. We call the generator equal to make generator model. We call the generator model. We provide it with noise and then we generate the images. So this is what it is actually showing, the grayscale images that are being generated by the generator at different steps. So you can see the checkered board effect here in these images due to the use of transposed convolution. Now we'll define the discriminator. So now discriminator is a very simple image classifier having only two classes, fake and real. So how those who are familiar with CNNs, how does a classifier work? You have multiple convolution layers stacked over each other. 8 minutes. So here again we define the discriminator model. It's a sequential model. We add a convolution layer. First convolution layer having 64 filters. Size of filter is 5x5. Stride is 2. Padding same. Input shape 28 cross 28 cross 1. Now here you see, because generator image कितने size की generate कर रहा था, 28 cross 28 cross 1. और जो हमारी रियल इमेजेस थी जो ट्रेनिंग डेटा सेट की, उसको भी हमने स्केल डाउन किया था 28 क्रॉस 28 क्रॉस 1 में. तो हमारा इनपुट शेप कैसा है इस मॉडल का, 28 क्रॉस 28 क्रॉस 1. Then we again apply, after convolution, we apply activation function. Then there is something called as dropout. I'm not talking about dropout right now. Otherwise, we'll move away from the topic. and we have a lot to discuss later. Then we again add a convolution, another convolution layer. Now the number of filters have increased 128, filter size is 5 cross 5. So here if you will see, the number of filters increases in a convolution neural network as we move away from the inputs. वहां पे क्योंकि हमारा फिल्टर्स एक्चुअली में क्या बता रहे हैं, अलग अलग फीचर्स जो हमने डिटेक्ट किए, जैसे हमने नोज डिटेक्ट की, वो एक अलग फीचर मैप है और वो अलग एक चैनल हो गया। फिर हमने आई डिटेक्ट की, वो एक अलग फिल्टर है, उसका एक अलग फीचर मैप हो गया। हमने टंग डिटेक्ट की, वो एक अलग फिल्टर है, अलग फीचर मैप हो गया। तो जितने अलग अलग फीचर्स हम डिटेक्ट कर रहे हैं उतने फीचर मैप्स बनते जाएंगे और उतने ही नंबर ऑफ फिल्टर्स हम यूज करेंगे। So in your classification model, the number of filters keeps on increasing. Whereas in the generator model, we have seen the opposite. The number of filters was decreasing as we move towards the output. और लास्ट में हमारे पास एक फ्लैटन लेयर है और एक डेंस लेयर है जहाँ पे हम आउटपुट करेंगे। तो यहाँ पे भी अभी हमने डिस्क्रिमिनेटर को सिर्फ डिफाइन किया है, हमने अभी उसको ट्रेन नहीं किया है। अब डिस्क्रिमिनेटर मॉडल को हम कॉल करेंगे। एक मिनट, हाँ, यहाँ तक हमारा पूरा हो चुका है डिस्कशन। नाउ हियर वी रन आवर डिस्क्रिमिनेटर मॉडल। जनरेटेड इमेज जो भी यानी जनरेटर ने इमेज जनरेट की वो हम पास करेंगे डिस्क्रिमिनेटर को और उसका डिसीजन हम देखेंगे। One more important thing is you need to define the loss functions and the optimizers. तो हमने बताया था कि हम बाइनरी बेसिक ज्ञान अभी मैं डेमोन्स्ट्रेट कर रही हूँ, बाइनरी क्रॉस एंट्रोपी फंक्शन यूज कर रहे हैं। So we use this inbuilt function, binary cross entropy function, which is already present in your tf.keras library. So now we define the discriminator loss. Here you can see. अब आप देखिए डिस्क्रिमिनेटर को हम रियल इनपुट भी दे रहे हैं, यानी रियल इमेजेस भी दे रहे हैं और फेक इमेजेस भी दे रहे हैं जो जनरेटर जनरेट कर रहा है। तो यहाँ पे हम डिस्क्रिमिनेटर का रियल लॉस भी कंप्यूट करेंगे और फेक लॉस भी कंप्यूट करेंगे एंड देन वी विल कंप्यूट द टोटल लॉस। नेक्स्ट वी विल सी द लॉस ऑफ जनरेटर। जनरेटर सिर्फ क्या करता है, फेक आउटपुट जनरेट करता है। तो जनरेटर लॉस तो सिर्फ फेक इमेजेस के लिए ही हमें कैलकुलेट करना है, जनरेटर को रियल इमेजेस से कोई लेना देना नहीं है। तो हियर वी ओनली पास द फेक इमेजेस एंड वी कैलकुलेट द जनरेटर लॉस। एक्चुअली अगर हम रियल गैन्स में देखें तो जनरेटर का कोई लॉस होता ही नहीं है, जनरेटर डिस्क्रिमिनेटर के लॉस को ही यूज करता है। तो उसके लॉस फंक्शन का वैसे भी कोई मीनिंग नहीं है या कोई रेलेवेंस नहीं है। देन वी डिफाइन द ऑप्टिमाइजर्स। अब बेसिकली ऑप्टिमाइजर का मतलब क्या है, ऑप्टिमाइजर मीन्स जो हमारा वेट अपडेशन प्रोसेस है। सो हम जो लर्निंग कर रहे हैं, ग्रेडियंट डिसेंट रूल जो यूज कर रहे हैं वो हमारा ऑप्टिमाइजर है। सो देर आर मल्टीपल वेरिएंट्स ऑफ ग्रेडियंट डिसेंट रूल। उन सब में सबसे पॉपुलर कौन सा है, एडम्स ऑप्टिमाइजर। तो when you go back home, some of the participants may be knowing about Adams optimizer. Those who do not know, you can Google it and see. This is the one of the most popular optimizer that is used for training or weight updation in your CNNs. So this again is an inbuilt function in your Keras library. You just call it, and both the gradient generator and discriminator, they use Adams optimizer for updating their weights. Now the parameter that you have passed here, 1 into e to the power minus 4, this is basically the learning rate that you have passed. Learning rate means how fast your weights will change. So this is just a hyperparameter used for training your models. So I hope up till this point it is clear. We have defined the generator, we have defined the model of discriminator, we have defined the loss functions, we have defined the optimizers that will be used by both generator and discriminator model. Now we will define the training loop. Training loop, as I told you, generator and discriminator, they learn in an alternating fashion. So let us see this code. I am skipping the above 3 lines because these will be called here. So what we do here is, I'll just move one line before. In this train step is one training step of your GAN. If you will see, we first take a noise vector from this random normal distribution and whose dimension will be noise dimension, that is 100 length noise vector. नाउ दिस टी एफ डॉट ग्रेडियंट टेप, ये जो टी एफ डॉट ग्रेडियंट टेप है ये एक फंक्शन है हमारे टेंसरफ्लो लाइब्रेरी में, जो एक्चुअली में जो बैक प्रोपोगेशन के पूरे कंप्यूटेशंस है, वेट्स कंप्यूट करना, ग्रेडियंट कंप्यूट करना, सारे जो फॉर्मूलेज आप पढ़ते हैं बैक प्रोपोगेशन में, वो सब चीज़ कौन करेगा, ये टी एफ डॉट ग्रेडियंट टेप फंक्शन करता है. So now actually we are generating images. So generated images is equal to generator. So now we are calling the generator model. तो आप देखिए जनरेटर मॉडल को हम इनपुट दे रहे हैं नॉइज, ट्रेनिंग ट्रू कर दी, ट्रेनिंग ट्रू यानी अब ये जनरेटर एक्चुअली में ट्रेन हो रहा है और इससे इमेजेस जनरेट हो रही हैं. अब हमने एक बार जनरेटर को ट्रेन कर लिया. नाउ वी विल पास दीज जनरेटेड इमेजेस टू द डिस्क्रिमिनेटर. तो डिस्क्रिमिनेटर को अब हम दो चीजें पास कर रहे हैं, एक तो रियल इमेजेस पास कर रहे हैं. तो डिस्क्रिमिनेटर के लिए देखिए दो स्टेप्स मैंने लिखे, डिस्क्रिमिनेटर इमेजेस ट्रेनिंग ट्रू, डिस्क्रिमिनेटर जनरेटेड इमेजेस. सो टू अ डिस्क्रिमिनेटर आई एम पासिंग बोथ रियल इमेजेस फ्रॉम माय ट्रेनिंग डेटा सेट एंड द जनरेटेड इमेजेस जो जस्ट अभी जनरेटर ने जनरेट की है. और डिस्क्रिमिनेटर अपना रियल आउटपुट और फेक आउटपुट दोनों निकालेगा और अपना लॉस कैलकुलेट करेगा. सो नेक्स्ट टू लाइंस में हम क्या कर रहे हैं, वंस वी कैलकुलेट द आउटपुट ऑफ डिस्क्रिमिनेटर ओवर रियल एंड फेक इमेजेस, यहाँ पे हम जनरेटर लॉस और डिस्क्रिमिनेटर लॉस कैलकुलेट कर रहे हैं. और ये जो लॉस फंक्शंस हैं ये हम ग्रेडियंट टेप फंक्शन को पास कर रहे हैं. और यहाँ पे एक्चुअली में अब ये जो ग्रेडियंट है इस लॉस फंक्शन का, जेन लॉस और डिस्क्रिमिनेटर लॉस, इसको यूज करके जनरेटर और डिस्क्रिमिनेटर अपना अपना वेट्स को या पैरामीटर्स को, लर्नेबल पैरामीटर्स थीटा को अपडेट करेंगे. ठीक है. सो दिस इज द स्टोरी ऑफ हाउ ट्रेनिंग एक्चुअली वर्क्स. हमारा जनरेटर अभी हमने डिफाइन किया, डिस्क्रिमिनेटर डिफाइन किया, देन वी कॉल द जनरेटर, उसको इनपुट में नॉइज दिया, ट्रेनिंग ट्रू किया, जनरेट सम इमेजेस. Once we have a set of generated images and once we have a set of real images, now we will pass both these sets to the discriminator. Discriminator output produce करेगा, अपना loss function calculate करेगा और ये जो लॉस फंक्शन है इसको यूज करके हम जनरेटर और डिस्क्रिमिनेटर दोनों के वेट्स को अपडेट करेंगे. ठीक है, क्लियर. नाउ अगेन हियर वी आर फॉर एपॉक इन दिस, वी आर जो हमने ये ट्रेन स्टेप फंक्शन जो अभी मैंने आपको जस्ट डिस्क्राइब किया, वी आर गोइंग टू कॉल दिस ट्रेन स्टेप फंक्शन फॉर ईच इमेज बैच. तो मैंने आपको बताया था कि ये हमारा बैच मोड ऑफ ट्रेनिंग है, हम अपने मॉडल को एक एक बैच के लिए सेपरेटली ट्रेन करेंगे. सो फॉर एपॉक्स, एपॉक्स मीन्स एक पूरा कंप्लीट रन ट्रेनिंग सेट पे. तो हम क्या करेंगे, एक एपॉक वन मीन्स इटरेशन. सो फॉर ईच इटरेशन फॉर ईच इमेज बैच मैंने 60,000 को डिवाइड किया था 256 के बैचेस में. एक इमेज बैच पास किया, ट्रेन स्टेप मतलब ट्रेनिंग की अपनी ज्ञान की, और ऐसा करके मैं पूरे 60,000 इमेजेस के लिए ट्रेनिंग करूंगी. Once done, then I am going to generate and save images that are used, that are generated by the generator. तो जब ट्रेनिंग कंप्लीट हो जाएगी तो आप अपने जनरेटर को देख सकते हैं कि वो कैसी इमेजेस जनरेट कर रहा है. And these are basically functions for displaying images. And I'll show this, ये वाला, just a second. So I'll show this train step. It is taking some time to run. Train function, the cell is already running and it will show you how the images are being generated. सो वन इम्पॉर्टेंट लेसन टू लर्न हियर इज कि आपको जो भी ज्ञान यूज करना है उसका जनरेटर और डिस्क्रिमिनेटर डिफाइन करना आना चाहिए, और फिर आपको उनके ट्रेनिंग कैसे करना है वो डिफाइन करना आना चाहिए। एंड देन बाकी सब तो जो आप डीप लर्निंग में बाकी कोड्स यूज करते हैं वही सारे कोड्स यहाँ पे यूज करना है फॉर इमेज डिस्प्लेइंग, फॉर एक्यूरेसी कैलकुलेटिंग एंड सो ऑन। One important thing that I missed to tell you is for evaluating GANs. GANs basically कोई simple classifier तो है नहीं जैसे आप normal CNNs use करते हैंगे. GANs are basically generating synthetic images. So we don't actually use accuracy, precision recall here. There are some special metrics which we use for evaluating GANs. And one of the most popular metric that we use is FID, that is Freshett's Inception Distance. तो अगर आपको गैन्स यूज करना है अपने किसी भी प्रॉब्लम के लिए तो, और उसका आपको देखना है व्हाट इज द क्वालिटी ऑफ इमेजेस दैट इज जनरेटेड बाय गैन्स, you can use FID. So FID, in fact, not only for GANs, for any generative AI model that you are using for generating images, you can use FID metric for evaluating the quality of GANs. एक minute each. Here it is showing. So see, now I will reduce the resolution so that it's visible. ये हैंग क्यों जा रहा है बेटा रन करते वक्त? So you can run the script and you can see actually the images it is generating at different epochs and the final epoch. So it is taking some time to run. I hope the code that I have discussed is clear to you. So shall we end here? Any questions? This code we'll share with you on the drive where we'll share this, or even you can find on Google Colab or TensorFlow website, not only of this DC GAN, for other variants of GAN like Pix2 Pix GAN, Style GAN, Stack GANs, all the codes they are available on the your TensorFlow website. Participants, so we will end the session now. Any questions, any doubts? So, Pratibha, shall we wind up? I think there are no more questions.
Yes, ma'am. Thank you, ma'am, for your detailed and insightful presentation on GANs. It has not only deepened our understanding for this fascinating technology, but has also opened our eyes to its immense potential across various domains. You have walked us through the foundation concepts, practical applications, and challenges of GANs, making it accessible and engaging for everyone. On behalf of everyone, I extend my heartfelt gratitude to you, Dr. Jain, for taking the time to share your expertise and valuable insights with us today. Your contribution has enriched our knowledge and will undoubtedly inspire us to explore and innovate further in this field. Thank you again, ma'am.
Okay, thank you so much, participants, for patiently listening and for the interactive